All right, 1.5 exponential function. Let's take a look. Let's start with a quick example. Right, the population of a place, a sub-Saharan African country from 2007 to 2013. So we're looking at a population of certain area. Let's see how the area is growing. You look at the increasing population in the third column, right? So we have change in population right here. All right, so let's start with 2007, 2008. So 2007 to 2008, it grew 0.425 million, right? 0.435 from '08 to '09, and so on. So you can see that the increase between every year is increasing. Right, not only the population is increasing, but the change in population every year is also increasing as well. Right. So it's not linear, right? Because if it's linear, then the change in population would be the same. So this is actually a popular application of exponential function is to calculate population growth. All right. So let's see. Here are some calculation. Right? If you look at every year, the difference. Let me go back a page. So if we look at this by subtraction, right, we know that this grew by 0.015. Actually, let me change the color. Right, it increased by 0. The increase amount is by 0.015, and this is 0.01. This is 0.01. Oh, actually, this is 0.1 as well. Right, and then 0.1. This is 0.09. Right. So the change is not the same, but the change of change is the same. Right. So how do we look at this? Right. So the way to look at it is we're going to take the ratio of the change. Right. Let's look at the next page. So population in 2008 divided by the population in 2007, we have here it's 14.660 divided by 14.235, which gives us a ratio of 1.03. And if we take 2009 compared to 2008, divide that, we also get 1.03. So that means from 2007 to 2008, it increased by 103%. And from 2008 to 2009, it also increases by 103%, and so on and so forth. Right? We can see that the population increase is always or around 103%. So let's look at the notes here. The fact that both calculation gives 1.03 shows that population grew by 3% between 2007 and 2008, and also between 2000 and 2009. Similar calculations for other years show the population increased by a factor about 1.3 or 3% every year. So an increase by 3% every year. Therefore, we have something called the exponential growth. If it's increasing by a fixed percentage, then we can say that this population or this data has an exponential growth. All right, let's keep going. If T is the number of years since 2007, then capital P, the population in millions, T years after 2007 is given by approximately this. All right, I'm gonna write it on the right. Capital P is 14.235 times 1.03 to the power of T. Right, so this part, 1.03 to the power of T, is what makes it an exponential growth, right? Because the base that we have here, 1.03, that's our base, the base growth, right? If it's above 100% or greater than 1, means it's a growing exponential growth. If it's between 0 and 1, then we say it's an exponential decay. Right? Since the variable t is in the exponent, this is an exponential function. The base 1.03 represents the factor by which population grows each year is called the growth factor. Right? In this case, the base is also called the growth factor because it's increasing every year by 3%. And increasing, that means we have to add the 3% on top of the 100%. All right, so here we have an example, mix and match. Right, so we have 6 graphs here and we have 4 parts to the question. We want to mix and match and see which one is which. So A, population increase at 5% per year. B, population increase at 8% per year. Population increased by 5,000 people per year. The population is stable. All right, so let's identify what type of function they are. Right, so if it's increasing at a fixed percentage, we know that this is exponential. Right, so it's increased by a fixed percentage, that's also exponential. Okay, now let's do let's see, A and B. Actually, let's do A and C. And I want you guys to try B and D on your own. All right, so population increased by 5% exponential. So exponential function, if it's increasing, then it looks like this, right? A curve that's going up, right? So we have 2 of them that might be exponential growth, which is 1 and 2. All right, so we have 2, that means one is 5%, one is 8%, right? So I guess if I give you one, you will figure out what the other one is. So let's do A and B together. All right, so 8% clearly is the one that's growing faster. Right, so comparing 1 and 2, which function do you think grows faster? When I say grow faster, you can, another way that you can think about this is which graph shoots up faster, shoots upwards faster? That's right, the answer is 1, right? 1 actually goes up much faster than 2, right? So this one would be the 8% one, right? And this one will be the 5% one. Given that these 2 are the only ones that look like exponential function, exponential growth function specifically, this one would be 8% and this one would be 5%. Okay, I want you guys to try the other 2 on your own. You can pause the video. All right, so increase by 5,000 people per year. So it's increasing by a fixed number, not a fixed percent. So if it's increasing by a fixed number, this one is actually linear, right? So we want to look for a straight line that's increasing, right? And the only one that is straight and increasing is line 3. This one would be part C, okay? And this is A, this is B, okay? The population was stable, means there's no increase or decrease in population, so it should be a flat line, right? And right here, that's part D. Okay. All right, so let's actually look at 4 and 6 because we don't have anything here, right? So 4, you can see that it's decreasing, but it's not a straight line, right? So 4, line 4 is what we would call an exponential decay, right? So in terms of population, when we talk about decay, that means we see people leaving the world, losing their lives, right? That's or maybe not so negative, but maybe leaving the country or move to other areas of the world, right? So an exponential decay would see a slower and slower decrease of population. Right? Eventually, it will become flat and no one leaves the place anymore. Whereas 6, that will be a linear decrease. Right? Every year, there's a fixed amount of people leaving the place. right? So what do you think is going to happen to 6 after so many years, right? Eventually it's going to reach 0, right? Eventually there will be no one anymore, right? Which is a pretty bad scenario, right? Imagine if uh, this is just for the sake of academic, right? For example, if there is a disease such as COVID that's killing a lot of people, right? If we see a linear decrease in people killed by COVID every month, then that is a really bad sign, right? Because that means we're going to keep losing people, losing loved ones, and eventually everyone is going uh, to log off because of COVID-19, which is a really bad case. But it's a great thing that we're not seeing this trend, right? And yep, population and exponential growth model, they are very popular among modeling type of population or people or viruses and stuff. Okay. All right. So this is a very important part. You want to have this written down somewhere, right? That is the standard exponential growth function, right? Where P0 is the initial quantity and A is the factor by which P changes, right? So A, remember, is our base or growth rate, right? It can be decay rate as well, depending on what you're looking at, right? And T is the time, right? So the factor A is given by 1 plus R, right? Where R is the decimal representation of the percent rate of change. R may be positive or negative, right? Positive for growth and negative for decay. So from our earlier example, we see a 3% growth in population. That means our A, our base, is going to be 1 plus 3%, which is 1.03%, right? Oops, 1.3%. Now, let's say we're looking at radioactive decay of uranium. Right? Let's say it's a 5% decay. Right? A decay means it's negative 5%. Right? So A will be 1 plus negative 5%, which gives you 0.95. Right? So to sum it up, if A is greater than 1, then we have growth. If A is between 0 and 1, then we have decay. Okay? What about if A is 1? Right? Then we have constant, right? Nothing changes. All right, so let's look at the bottom here. A linear function has a constant rate of change. An exponential function has a constant percent or a relative rate of change. Okay, so that's the main difference between linear and exponential. All right, so one common base that we'll be looking at is the number E, Euler's number. It's about 2.71828 or 2.72. There is a button you can find on your calculator that just says E, right? That's the button you can use if you want to use a calculator for some calculation, right? So E is right here between 2 to the T and 3 to the power of T. This is E to the power of T. In most commonly used base is the number E, right? As we'll see in a second. And if you're interested in how E is the most common number for the base of an exponential function, feel free to take Calc 2, right? And imagining if you are taking this one, you don't need calc 2, but you know, just in case if you're interested, you can go into my YouTube channel. I do have videos for Math 1150, and there is one video that talks about the number E. All right. All right, so here we have a quick example of decay, exponential decay. So as you can see that the main difference is that it's going downwards in sort of like a curve. Right, so if it's 0.95, it's decreasing slowly, but it's 0.1, then it's decreasing very fast, right? So the closer you are to 0, the faster you are decreasing. Right? So it's just a nice graph to show the main difference between growth, right? Growth, you're going up, right? Depends on what your base is, how fast you're going up, and decay, right? Depends on how close you are to 0, how fast you decay. Okay, we're here looking at our first problem from 15. A 50 milligram dose of quinine is given to a patient to prevent malaria. Quinine leaves the body at a rate of 6% per hour. Okay, so before we look at each part, let's understand what we're looking at here. All right, so I'm taking quinine, 15 milligram, right? And every hour, I lose 6% per hour, right? 6% per hour. Q, right? And so on. All right, so if I'm losing a fixed percentage per hour, is that an exponential decay or a linear decay? That's right. If we are looking at fixed percentage, that means this is an exponential decay. Right? Another way that you can know that this is exponential decay is this section is called exponential function. That's kind of dumb, but yeah, it is. All right, so that means what we're going to be using is the standard function that we looked at earlier, right? Capital P. Oops. Capital P is equal to P naught A to the power of T. Okay, so all we need to do is figure out what they are, right? This is part A. Find the formula for the amount of A in milligram of quinine in the body T hours after the dose is given. All right. So I guess we should be using A, not P. Okay, so P naught, P0 is the initial amount. So what's the initial amount of quinine that's given? Right here, right? 50. That's initial value. 50. Okay, now A, to find A, that's the interesting part. First, we need to figure out what R is. What is the rate of change, the percentage change per hour? It's right here, right? It's leaving the body. So that means the quinine in your body is decreasing at 6% per hour. So I'm looking at negative 6%. All right, so A, little a, is going to be 1 plus negative 6%, which is 0.94. Right, so A is 0.94. Okay, 0.94 to the power of T. Okay, so that's the answer for part A. The formula for the amount of quinine in the body T hours after the dose is given is right here. Capital A is equal to 50, the initial dose, multiplied by 0.94. That is our decay rate, right? Found right here, right? 0.94 to the power of T. All right, and I want you guys to pause the video, take a few minutes to figure out what B, C, and D are. All right, so how much quinine is in the body after 24 hours? You just let T be equal to 24. All right, so A is equal to 50, 0.94 to the power of 24. And I get something that's around 11.33 milligram. Okay, so after 24 hours or after a day, you still have about 11.33 milligrams of quinine in your body. All right, C, graph A as a function of T. Right, it's right here. Right, you can use any graphing tools. Right, Wolfram Alpha, GeoGebra, Desmos, or a graphing calculator. Right, and D, use the graph to estimate where 5 milligram of quinine remains. So 5, it's about here. All right, right here, about 36, 37 hours. Right. Actually, now we don't have the tools to solve it, but if you remember natural log from algebra, you will be able to solve this. Right. But for now, we can just give a rough guess using the graph. All right, let's keep moving on. Section 1.6, the natural logarithm or natural log or ln. All right, ln, that's your natural log. All right, so let's take a look. The natural logarithm of x is written as ln x. All right, ln of x. Oops. Ln of x is the power of e needed to get x. In other words, ln x equals to c, or some constant, is the same as e to the power of c is equal to x. The natural log, sometimes written as log base e of x, is called the inverse function of e to the x. ln x is not defined if x is negative or 0. Okay, so keep that in mind. The domain of ln of x is strictly positive. Right? X has to be positive, not 0, positive. Okay, so I'm pretty sure all of you have seen this before in your algebra classes. So let's just keep moving on. All right, so here we have some properties of natural log. Right, we have the product rule. All right, let me make a note here. First one is the product rule. All right, the quotient rule, the power rule. All right, and these two are the identities, or the log, natural log to exponential identities. In addition, ln1 is equal to 0 because e to the power of 0 is 1, and ln of e is 1 because e to the power of 1 is 1. Right? Let's just do a quick review, quick example on all of them. So the first one, let's say ln of 3xy can be written as ln of 3 plus ln of x plus ln of y, and vice versa, right? You can go forward or you can go backward. All right, 2, if we have ln of xy over z, right? So notice here, I can write this as ln xy minus ln z. But see, furthermore, I can split this ln of xy using the quotient rule. So I can write this as ln x plus ln y minus ln z. Right? And the last one, power rule, it means if you have any power in the ln, you can put it in the front. But notice here they have different powers, right? So we have to split them up using the first rule, the product rule. And then we can bring the power of x and the power of y to the front, like this, right? So 6 to the front, I get 6 ln x plus, put the 7 in the front, 7 ln y. Okay, so some nice properties we have for the log. All right, let's look at one example, solving equations using logarithm, right? Even though the solution is here, but I'm not going to go over this. I'm going to show you how to do this from scratch on the right. All right, 3 to the power of t is equal to 10. All right, so we know that the opposite of exponential is logarithm, right? So what we're going to do when we're solving these kind of equation, when you see a variable in the exponent, immediately think about the opposite of exponent, which is log, right? And which log are we going to use, right? We are going to use a natural log because it's easier to use and less to write. Instead of writing log, you just need to write ln. All right, so first things first, we're going to apply log or natural log on both sides. Oops. So ln of 3 to the power of t is equal to ln of 10. Now, keep in mind that ln of 10 is just some number, right? You can type that into the calculator and it will give you a number back. So this is a constant, right? ln of 10 is a constant. Right? So we're not going to worry too much about it. We're just going to leave it in the form of ln. All right, now on the left-hand side, I'm going to do is I'm going to apply the power rule, means I can take this t, oops, and bring it to the front. So I get t times ln of 3 is equal to ln 10. Now notice that ln of 3 is also a constant, right? So what we can do is we can just divide ln of 3 on both sides, and we have solved for t, right? So t is ln of 10 divided by ln of 3. Now, don't worry about the exact value of this. We can just leave it in the form of ln, right? So you can leave your final answer in ln of 10 over ln of 3, right? So here, you actually use a calculator and gives us that t is 2.096. But, you know, either way is fine. If you like putting this way, that's correct. If you like putting into a calculator and find out the exact value, that's also fine. All right, let's move on. All right, so here we are going to look at two different types of growth. We have annual growth or continuous growth or decay, right? So earlier we saw this, right? The first one. That is for an exponential growth or decay, right? Depending on it's annually or a monthly or hourly or whatever. Right? But we are going to use this one for a continuous growth or decay. Okay, and the problem will tell you if it's continuous growth or decay, or if it's annual decay. Right, continuous growth means it's always growing. Right, it's always growing. So let's see. What annual percent growth rate is equivalent to a continuous growth rate of 8%? All right, so here we're actually given the relationship between a and e to the k, right? So we're comparing the base a and e to the k right here. So let's see. Annual percent growth rate means we want to find out what a is. It is equivalent to a continuous growth rate of 8%, right? So here, continuous growth rate, we have k is equal to 8, right? And we also know that a, from up here, a is equal to e to the power of 8, right? There we have it, right? A is e to the power of 8. And then you can punch that into your calculator, and that gives you a really big number, 298.0.9596, right? A huge number, right? But that's fine, right? So that's basically it. What continuous percent growth rate is equivalent to an annual percent rate of 10%? Okay, I want you guys to try this one on your own, okay? All right, so here we are trying to find k, we want to find K, right? So K is actually ln of A, right, as we see up here, right? So A is going to be 1 plus the annual percent growth rate is positive 10%, so it's positive 10%. That is 1.1, right? So I'm gonna move it to the right hand side. So K is ln of 1.1, which is 0.0953. Okay, and that's it. And usually the question will tell you whether they are looking at annual growth rate or decay rate, or continuous growth or decay rate. Rarely we would convert between annual and continuous growth rate. All right, so here we have some quick example on looking at graphs and sketching graphs. So sketch the graphs of PAZ to the power of 0.5t. This is growth rate. And Q is equal to 5 times e to the negative 2t. All right, so before you're looking at the graph, if this value K is positive, it means it's a growth, right? If K is negative, then that means it's a decay, okay? So you can see that the first one is an exponential growth and Q is an exponential decay. Now this is continuous growth and decay. We're not looking at annual anymore. It means the standard formula that we're looking at is P is equal to e to the KT. Okay. All right. Point out a few more things. All right. It's starting at 1. Right here, it's 1, and it's growing exponentially at 50% continuously. And for Q, is decreasing. And notice that here is a 5 before the E, right, which is your P0. Oh, I forgot the P0 here, the initial value. All right, so initial value is 5, and it's decreasing from that point on. Okay? So just some quick graphs, looking at graphs. So a few things that you want to know from the graph is understand whether it's showing a growth or decay in terms of exponential functions. Another one is knowing how to identify the initial point, right? And the initial point is always at t equal to 0, right? The y-intercept. That's always the point you start. And then you either go up, increase from there, or decrease from there, okay? All right, and that will conclude these 2 sections, and see you next time.